Hi everyone, welcome to my channel and welcome to this new video. So in this video I'm going to implement one of the first games I ever played on a mobile device, on a monochrome mobile device, and that is the Snakes game, the classic Snakes game, right? I believe it belongs to the category of the oldest mobile games because that time you only had those monochrome displays, and then there were different versions of this game wherein people implemented 3D versions of this game. There were colorful versions as well, but the classic Snake in my mind is still the old monochrome one where you would draw the snake pixel by pixel on the monochrome display and you make it move, and then the snake would move, it would turn, and there would be various modes of the game, like one with the timer, one with obstacles and things like that. So the basic concept is like there's a tiny snake which is going around in the screen. You can control its movement, right? Using up down, you can make it go up, down, left, and right. No diagonal movements, and from time to time, actually not from time to time, every on at any given point of time, there would be a particle of food. Like you can consider it as a simple particle, but in reality, it's a food. Like in the game world, it's the food for the snake, and the snake has to go and eat that food. Basically, by eating, I mean, you just need to take the snake and make it collide with the food particle, and that's it. Like that signifies that the snake is eating the food particle, and whenever it eats food, it grows in size, right? And that's the fun. Like the snake slowly starts growing in size, and then comes the challenge of controlling the snake, because if the snake goes out of the boundary, two things might happen. It can either wrap around, it can enter from the other side of the screen, or in some cases you just die if you try to go outside the screen boundary. And the other challenge that you will face once a snake grows in length is when you are making turns and things like that. If by mistake the head of the snake, that is the front part of the snake, collides with its own body, it means that the snake is trying to eat itself, and the snake dies, which means it's game over, right? So yeah, that's the basic concept of the game. Like you need to control the snake, feed it grows in size, you need to control it should not eat its own body, it should not go outside the screen boundary. That's pretty much it. And if you think about it, and we'll get into the details of it, like even though it's a fun implementation, it's really a fun implementation. Once again, I'll be doing it in Raylib, although I could have done it using terminal graphics like using ASCII, but I decided to go with Raylib since that's what I mostly use when I'm doing things in C. So I'll be doing this in pure C as well. And once again, this game is a perfect example of using a linked list in real life, right? We'll soon get to know how we can use linked list in a very cool way to represent the body of the snake and to make it move and things like that. And the other thing that I'm going to do it is I'm going to, instead of drawing shapes directly on the screen as is and make it move by increasing or decreasing by changing its x or y coordinate, I'm going to do something different in this case. So what I'm going to do is I'm going to divide the screen into a grid of cells, right? So the screen will consist of multiple small square, perfectly square cells. So it becomes basically a row cross column grid, and I'll shade those, or I'll color those square black whenever I want to draw something on the screen, right? So basically, instead of dealing with pixels, I will be dealing with squares, or I will be dealing with cells. And you will soon see that. So this not only gives the game a retro feel, but it also, this one tiny trick, this will also help you in controlling the snake body movement. You'll soon see how it will help us controlling the movement of the snake. So how we can manipulate the snake movement and the turns when the snake is taking turns and things like that. How it becomes easy if we consider the world grid of cells, and the body of the snake as well, composed of multiple cells or a collection of cells, right? Then how we can track the movement of those cells to make the entire snake move, and it will be pretty fun to implement that, right? Okay, so yeah, as always, without further delay, let's get started. Okay, so before jumping into the implementation, let's try to understand a bit more about the grid concept and how we can use the cells to simulate the world of the snakes game, right? So usually what we do is if we create any game object in Raylib, let's say it's any entity, like let me just theoretically refer to this object as some object called E, or game entity E. So usually it will have two coordinates. Basically, it will have an x coordinate and a y coordinate, x comma y. This x comma y would define its position in the game world, which is this 2D screen. And if you want to move it towards right, you do x plus equal to 1. If you want to move it left, you subtract from x. Same with y for moving up and down, right? Sorry, down and up, because in digital screen, when you subtract from the y coordinate, things go up. When you add to y coordinate, things go down, right? And the origin is located at the top left corner. So now what we are going to do here is that, let's say, yeah, Yeah, so let's say this is our screen, and what we are going to do is we are going to divide this screen into a grid. Okay, so we have our grid. We divided our screen into grid like this, and each cell would be a perfect square. And so now the fun part about doing things like this is that whatever object we would want to draw on this in this screen, or whatever object we want to define, it will be nothing but a collection of such cells, right? In such a case, the body of the snake. So initially, the snake will start as a single, just a square like this. Initially, it will be a square like this. The food particle will be another simply square or another cell. Whenever, let's say, the snake eats this food particle, it will increase, its body size will increase by one cell, and let's say it will become something like this, right? It will become two cells. It eats another, let's say it eats another food particle, and then it will, another cell will get added to the body of the snake, and so on and so forth. And the length of the snake will keep increasing. Now, the fun part is when the snake is going in a straight line, and you do not press any keys on the keyboard, let's say it's going towards the right and you do not press up or down arrow, it goes in a straight line. But what if you press down arrow in this case? Let's say the snake is going this way towards the right, like snake is traveling towards the right direction, and this is the front part of the snake. And at this point, at this particular square, you want to make the snake go down. So what happens is that the moment you press the down arrow key, the head of the snake will go to this cell, right? It will start going like this, then it will come to this cell, then it come to this cell. Now the fun part is, so this cell, when the head of the snake just went down by one cell towards the downward side and it occupied this cell, the tail of the snake, or this the body of the snake, or this cell in its body, or this cell in its body, in its world, it's still going this direction, right? At this point, when this cell of the snake's body is in this particular position, or this part of the snake's body is in this particular cell, it doesn't know that it has to move down. It needs to keep traveling towards right. It cannot suddenly go down from here, but it has to travel in this direction. Only when it reaches this corner, it needs to go this side. When this cell, let's call it the cell X, when the cell X travels to this corner, X cannot go this way. X needs to go to the cell which is one cell down towards this direction, towards the down direction. It cannot go towards right. Now imagine, let's say we have a very long snake. Suddenly, when the snake head is here, the tail is still here. This is, call this cell of the snake's body as the tail cell, okay? And this as the head. This is the head cell H. Now, when it's in this particular cell, when the head of the snake is in this cell, you suddenly decide, or the player decide that the snake needs to go towards the right hand side or towards the right side, and you press the right arrow key. So you are expecting that the snake will go this side, towards the right side. So now the head goes this side. So head now comes here, then here, then here. So now just imagine the tail, how the tail cell of this snake behaves. It has no clue that the head has gone this way. So, and it doesn't even have a clue that after this cell, it needs to go down. So what needs to happen here, when T comes here, it cannot go this side, but it needs to move this side. It needs to go down. And again, when T comes to this cell, it cannot keep going down, but it needs to make the choice, or it needs to take the decision, or it needs to update its movement to, or its direction of movement to go this side, towards the right side. So just imagine a movement like this for a pretty long snake. So the tail, or any part of the body, it always has to make these directional changes whenever it reaches the corner cells, right? Whenever it reaches the corner cells, it needs to make a update in its direction. And this is what adds the challenge as well as the fun in implementing the snake's movement, right? This is where it no more remains a normal game object update using X and Y coordinate manipulation, but you need to think a bit more into this and how you can control the body of the snake when it moves, so that it moves in a proper trail. If the head of the snake moves from a particular point, all the other body parts should follow. It should maintain the trail, and exactly when it reaches that point in the grid where the head made the turn, it should all the remaining cells of the body should also make the turn at that particular point, not before, not after, but exactly at that particular corner. So one very naive implementation that would come to our mind is that we track the direction of movement and XY coordinate of each and every cell, and we somehow store whenever the player hits a direction change or makes a change in direction. And whenever that particular cell reaches that particular position where the user had entered something, we store the direction as well as the corner position where the player had made the direction change. And whenever any cell in the body of the snake reaches that particular grid cell, that particular cell in the grid where the player had changed the direction, we make a change in the movement of that particular cell, and the others follow. So this makes it pretty complicated. You are storing the corner cells, you are storing the player's choice of direction and all those things, right? But if you take a step back and think about how this entire body of the snake is going, you will see that there is a pattern. And this is where this method of treating the world as a grid and the body of the snake as collection of cells comes really handy. If you see, when the head of when the head position of the snake gets updated, just the previous, let's consider that the head is here right now, and we update the position of the head to the next cell, that is this one. So the head comes here, so this was H, now H comes here. All that the previous cell in the body of the snake needs to do is occupy the previous old position of the head, because the head's position has been updated. Head's new position is this, right? This is head's new position. All that the previous, just the cell previous or the cell just next to the head needs to do is now occupy the old position of the head. And similarly, the cell which was before this cell, which is this cell, let's call it C1 and let's call it C2. So C1 now goes here, this becomes C1, and H is here. So what C2 needs to do is occupy C1's previous position. So if you apply this theory, or if you apply this technique to all the cells in the body, each and every cell, what it needs to do is occupy the previous position of its next cell just blindly, nothing else. One thing needs to be true is that the head of the snake needs to keep moving. Otherwise, this thing fails, right? If the snake is moving, it means the head of the snake is continuously changing position or changing cells. If the position of the head of the snake is changing, all that the cell next to it, that is C1, needs to do is occupy the previous position of the head. And all that C2 needs to do is occupy the previous position of C1. And similarly, all that Cn, like basically all that Cn that any given cell in the snake's body needs to do while in order to move is occupy the position that was previously occupied by Cn minus 1. That's it, right? So at any point of time, cell Cn will try to occupy the position that was previously held by Cn1. Cn1 will update its position with the position of the cell previously held by Cn2, and so on. And if each and every cell of the snake's body blindly follows this algorithm, you will get an effect that the snake is moving forward, right? And the beauty of this method is you don't need to cheer at what point or at which cell the snake made a bend or the snake made a turn, because all the previous cell needs to do is occupy the previous position of the next cell, right? The cells don't care about which direction they are going, where they are going. All they are doing is they are just copying the movement of the previous cell or the next cell, however you call it. Like I'm calling here the previous cell, you can call it the next cell. Is just a straight line, right? So doesn't matter how zigzag turn you make, like you are going like this and this. All this cell needs to do is update its position to this cell. This cell needs to update its position to this cell, this to this, and so on. And a very nice chain effect gets created, which gives us the illusion of, it's not an illusion, which actually makes the cell as a whole move forward or along any trail of your choice, right? So that's an advantage we get of using this cell-based design, and how we can move the snake by treating the world as a grid. As I mentioned, although the snake game is a pretty simple game, the implementation has this beauty hidden in it, and it's not that trivial. It is easy to implement. It's pretty easy to implement. The core part of the code that implements the snake movement hardly takes 4 line or 3 lines of linked list manipulation once you know that this technique, and it's really fun to implement. So that's how we are going to implement the snake body movement. And there is another hidden detail here. How do you add a new body part or a new cell to the snake's body, right? That needs to happen whenever the snake collides with a food particle. So let's say this was a food particle, right? So the snake comes here, then here, then here. The moment it collides with this one, the total body of the snake should get increased by 1. Now the question comes, where do you want to add the new cell? You could have added it here, that is also correct. You could have added it here, and you could have added it here. But the correct one should be here, because we want to maintain a trail, right? This adding a cell here would mean the player made a direction change at this point, which is not true, right? The player did not make a direction change here. So the thing is that you need to follow the trail. One correct possibility could be this cell. But again, think about it. What if the snake is something like this? Like let's say this is the current configuration of the snake. The tail is here and the head is here. Now where would you add a tail cell? It will go out of the screen, which is not correct, right? Technically it's a game over situation. If, like, in this game at least, we are considering that it's a game over situation, or and in many implementation of snake, it's like game over if any body part of the snake is outside the screen, right? So you cannot literally add here. This is not correct. So where would you add the new cell in the snake's body? One very easy way to do that is add the new cell towards the head of the snake, right? So what we basically do is add a new head for the cell. By that, what I mean is that, let's say the food particle is here. For a let's consider for this example, the food particle is here, or let me just say denoted as F, right? So this is our food particle. So the head of the snake is here, and obviously what the player would try to do is it would hit the down arrow to make the snake go downwards. So let's say the snake comes here, right? And what's important to check that in this position the player has not pressed left or right, right? In that case, the snake wouldn't reach the food particle. So in this frame, when the snake's head is in this cell, just above this, the food particle one, and in the game loop we have already evaluated the inputs. So in every game loop, in every iteration of the game loop, you evaluate the input keys pressed once, right? After that, you update the position of your objects in the game world. So just after you have evaluated the input provided by the user, you check if the next logical cell for the head to go to is the food cell or not. This we can very easily find out if after the input has been, in this case for example, we can make sure that the player has not pressed left or right, which means the next possible position of the head is this food cell. So what you do is you add a new head cell here in this cell. You add a new head cell for the snake, you attach it to the snake body, and let the course of the program follow, which means the head goes here, then here, if the player has not pressed anything else, right? Again, so that's a clean and a easy way to increase the length of the body by adding new heads to the snake instead of adding a new tail to the snake's body, right? Again, it will be clearer when we start implementing the logic for this. For now, this is how we are going to implement the world of the snake game, how we are going to convert the world into a grid, and how we are going to implement the snake body and its movement cell by cell by assuming that the body of the snake consists of several cells. Here by cell I mean these small squares in this grid, and the food particle or any entity would be a collection of cell or squares in this case, right? So yep, now let's get started with the implementation. Okay, so here I have the usual Raylib template that I use, and let's quickly try to make sure that it builds and runs. So yeah, I get nothing but a blank screen, a Raylib window. Okay, so the first thing that I'm going to do is I'm going to set the screen dimensions. That's very important. So the dimensions will say how big will be the grid, and the dimensions of the grid will tell us how many cells we will have. Actually, not just the dimensions of the grid, but the dimensions of the grid and the dimension of individual cell. So let's decide on that first. For this snake game, which I'm calling dot snake, as you can see, what I'm going to do is that I'm going to consider the screen width as 800 and screen height as 600. Now this is completely up to you, right? You could go for the traditional mobile screen type as well, where it will be a long rectangle or a horizontal rectangle, something like that. I'm just going with 800 cross 600. And now the cell width. So for this dimension, I felt that taking a cell width of, so again it will be a square, width and height will be same, but I'll still consider width and height separately as separate variables or separate macros. So I'm going with a cell width of 20 and a cell height of 20 as well. If my screen width and height is already defined and my cell dimensions are also defined, I can now get the number of cells along the x-axis and number of cells along the y-axis. So let's do that. Num cell x equal to screen width by cell width, and I'll define game states, although we'll be reaching to this portion way late in this video, but still I'll just define it right now. I'll have a game running macro and game over macros. So these are just macros to define the state of the game or the stage of the game, whatever you call it, right? So that's pretty much it for the starters. And there's some more things we'll need, but first let's just use these dimensions to set up our grid. So I'll get rid of these. We don't need these. So I'll use screen width and screen height. I'll call it, let's make it caps dot snake. And now what I'll do is, okay, this is very obvious. I'll remove this comment. So now if I run this, okay, I want to do one more thing. I inside the drawing loop, the first thing I would want to do is I would clear the background and I'll set it to white. White still black. I don't know. Let's check once. So I already had one written below. Yep. Now we have a white window. And now what I would want to do is I want to draw the grid for the starters. So what I'll do is I'll take two variables, pos x equal to 0. It's just simple grid drawing, nothing fancy. For pos, actually I don't even need these variables to be defined here. I can, because after once I'm done there is no use for these variables. So I'll do int pos y equal to 0, pos y less than screen height, pos y plus equal to cell height, right? Because at every cell height we will draw a horizontal line, basically what it means. So we'll increment the pos y variable by cell height so that it creates a gap equivalent to cell height units, and then we'll draw horizontal line. So draw line zero comma pos y. So it'll start from the topmost horizontal line and we'll go one by one to the down towards the bottom of the screen. To screen width. So x coordinate becomes screen width at the far right of the screen. So it's a horizontal line, right? It begins from the starting of the screen, which is extreme left to extreme right. To pos y and pos y. So basically, along horizontal, like when we draw a horizontal line, the y coordinate remains same and the x coordinate only changes. And we'll choose a color, and the color shall be, actually for now, you know what? Let's call it black. Let's use just black. And for the vertical lines, it's pretty much the same. Actually, I don't even need to. Okay, let's go with the naming conventions. Let's not just use a variable I. And this time we'll draw horizontal lines. So for we'll draw vertical lines this time. So for vertical lines, only the x coordinate changes, but the y remains same. So we'll start with pos x, and this is 0. 0 means topmost part of the screen. 2, it goes screen height. The first coordinate of the second point would be pos x, as I said. For vertical lines, x remains constant, only the y coordinate changes, and this will of course be screen height. Let's see, it should be able to draw us, we should be able to see our grid now. Make run, and we have our grid, right? So each cell will now represent something in our game world. It can be a cell for the body of the snake or for the food and things like that. Okay, let's now go back to defining some more variables for our game world. So one thing which we already discussed, we need to track the direction towards which the snake is heading, and the snake can head only towards four directions: up, down, left, and right. And we also need to track this direction when the player interacts with the left, right, up, and down arrow keys, right? And because that will change the direction of the snake. So we will do cur dir equal to for now we will initialize it with a value called 3 y3, because right now for this game I'm making a convention that upwards is 0, and from there we go anti-clockwise. So up means 0, left means 2, down means, so sorry, up means 0, left means 1, down means 2, and right means 3. So that's 0, 1, 2, 3. Four values for four directions. And in the start, we always want our snake to move right. Okay, then comes certain type definitions. So first we need a structure to define the cell. Now whatever structures I'm going to define next shall put into the to represent the body of the snake. So next, whenever I'm using the word called cell, it has got something to do with the body of the snake, right? So basically what the convention I'm following is the body of the snake is consists of several cells, and each cell will have a the main property that every cell will have is basically x and y coordinate, basically a vector 2 pos kind of a variable, like really out of the box provides us with a struct called vector 2. Vector 2 has got only two objects, which is x coordinate and a y coordinate. So we will use that, and the cell will have only this property, which is vector 2. So yeah, that's pretty much what a cell is. Let's define it. Type def struct cell vector 2 pos, right? So that's a cell. Now we will represent the body of the snake as one of my favorite data structures, that is the linked list, right? So what a linked list consists of, it consists of nodes, and what will each node consist of? In this case, it will consist of a cell. So the nodes of the snake linked list will pretty much have two properties. One is the cell, another is the next pointer to the next cell node. So for that, what we'll do is we'll create a struct called cell node. We will call it cell t cell struct cell node star next. We will type this one as well. Now, the most important thing that every linked list has is a head node. And obviously initially it will be null. And we also need to get some more header file inclusions. We need time, we need stdio.h, and we need stdlib.h. Okay, now some usual linked list functions that we need to quickly implement. So we'll have cell t create cell, some linked list, actually some linked list helper functions, I should say. Here we just instantiate a cell or struct of type cell, and we initialize with the position that we get. Next, we want to create a it's a helper function to create a cell node. So first, basically, we'll malloc a cell node, and that node's cell property will be initialized with the cell parameter, and cell node dot next equal to null, and then we return the cell node. Next, of course, a helper method to add a new cell. So remember, we will never add a node to the end of the linked list. We will always add a node to the head of the linked list. That's how the eating of the food effect will come into picture. Whenever the after evaluating the input controls or the inputs, the key inputs, we see that the next cell that the snake's head will go into is a food cell, that the cell that contains a food. Here, by cell I mean the cell of the grid. If that cell contains a food, what happens is that the cell node becomes the new head of the snake. So basically we had add a new node for the snake linked list, and the new node becomes the head of the linked list, and that head node becomes that cell, that the head node gets placed in that food cell, right? And that becomes a new head, and the snake continues from there. So we will never add a cell node to the end of the snake, but always we will manipulate the head of the snake. So first there is a base case. if the existing head is null, this is mostly when the game is starting or restarting, right? So of course we'll create a cell node and we'll pass the cell variable or param that we got. So we'll initialize the new cell node with the cell, the given cell, and we'll return. Next, what we do is, otherwise if it's an existing linked list, then we will update the head. But again, adding a new head is pretty easy in a linked list, in a singly linked list, even in a doubly linked list as well. Now we have got the new node. We set is next to the existing head, and we set the current head node to the new node. Now let's take a pause and let's try to draw a single cell snake and see if we are able to move it around cell by cell. What I'm going to do is I'm going to come down to my main method. Before that, what I'll do is I'll create a method called void init game. And here what I'll do is first I'll add a cell at a predefined position, because init game is when the game is starting for the first time, or when the player has hit game over and we are restarting the game. We'll come at the end how can be game over and what are the conditions for that. For now, let's just, for the starting position will be 4,4. It's just a random thing I chose, and we'll set dir to 3. That's pretty much it for now. This much should be enough to for the current implementation of the init game function. So now what I do is I do a init game, and here just before clear background white, actually clear background white should be at the very beginning. It should be at the end. Yeah, let's put it somewhere here. What I'm going to do here is I'm going to run a while loop. First I'll do cell node t star temp equal to cell node head, and then while it's normal linked list iteration or traversal, that's it. While temp not equal to null, draw rectangle temp dot cell dot posx. So remember, when you are drawing a rectangle, the parameters are the coordinate of the top left corner of the rectangle and the width and height of the rectangle. Since here width and height is same, it will be a square. But not just dot x in this case. We can't only just give the x coordinate of the top left corner, we also have to scale it, because remember, x by coordinate here we won't be meaning the actual coordinate on the screen system, but here coordinate means a particular cell on the grid, right? So if we say 0 comma 0, it doesn't mean the 0 comma 0 point, that is a top left pixel on the screen, but the top left square or the top left cell on the grid. So it basically becomes the top left square. Similarly, if I do 1 comma 1, it doesn't mean the 1 comma 1 pixel, but the square or the cell located at the position 1 comma 1, if we consider the grid as our coordinate system. So we need to scale it. So for that, we'll simply multiply the coordinates by cell width into cell height. So that's our width and height. Sorry, that's our coordinates, then cell width, and finally cell height. And I want it to be black. Now, of course, we need to update the iterator. So that becomes temp equal to temp dot next. That's all we need to print all our entire snake body, which right now is nothing but a square. And in order to have that, one thing we need to do is we need to yeah, we have already called init game, so that's fine. So let's see, we should ideally what we should get is a square at 4,4 cell of the grid, and we did get a painted black cell at 4,4. Why is it 4,4? 0 1 So let's see the x coordinate. So x coordinate 0 1 2 3 4, and so 4, y coordinate 4 means we need to shift 4 cells down, 0 1 2 3 4. So 4 comma 4 is actually 5 comma 5 because it's 0 indexing, right? So we are able to draw a basic cell or paint a basic cell black. Now let's move this square, right? Let's move this square and let's add code so that we'll be able to control the direction of this cell or direction of the snake here. So for that I'll create a function called update cell positions. So just imagine if the cell is moving up, then where does the head, which is the next cell that the head goes to? The head next goes to the cell which is immediately above it, right? And what does that mean in terms of the coordinates of the head? So basically it goes y just becomes y minus 1, but x remains same. Similarly, when it's going towards left, going towards left means immediately to the cell which is on the left hand side of the head, and that means x minus 1. The new coordinate would be x minus 1, y remains same. Similarly for right it becomes x plus 1, y remains same, and for down it becomes y plus 1, but x remains same, right? So up means y minus 1, left means x minus 1, right means x plus 1, down means y plus 1, right? So from here we can calculate the del x del y. So if we can calculate the del x del y from the direction it's heading towards, then we can simply add that del x del y to the current head's coordinates, and that would become the next new position of the head. So let's do that. Del x del y equal to 0 if if curve dir equal to 0, del y equal to minus 1. So we are not updating the head's position immediately, right? We are just calculating the delta. So if existing direction is 1, if that is if the snake was already heading towards left, so the next position would be, so the next for calculating the next position, del x would be minus 1. Right? So if it's moving up, then del y equal to minus 1. If it's moving left, then del x equal to minus 1. If it was moving right, then sorry down, then del y equal to 1. If it was moving right, then del x equal to 1, right? So what's the new position of the head? That's vector 2 dot x equal to cell node head dot plus del x, and dot y equal to cell node head dot cell dot pos dot y plus del y, sorry del, yeah, del y. Okay, now comes the other fun part. How does the snake move? We have calculated the next position of the head, right? So the head's new position is sorted. It's sorted and it's all good. How do we calculate the positions of the other cells of the body? Right now our snake is just a single cell, right? But soon we'll be adding food particles, and then the snake will eat the food particles. It will grow in size from head. And then how do we then manage the movement of the other cells of the body? And which, this is the very thing that we discussed earlier on using our drawing board. What we will make each and every other cell of the body do is occupy the position of its previous cell or next cell, however you want to picturize it. So basically when the head moves up, the h minus 1 cell would occupy the previous position of the head, the h minus 2 would occupy the previous position of h minus 1, and so on, right? So here I'm pretty much going to implement that, and since we are using a linked list, it will be pretty simple to implement that. It's only going to be a 4 to 5 line functions. So while temp not equal to 0, so with what is temp? I never defined temp, my bad. Cell node temp equal to cell node head. So for every every cell now we will have a variable called pref pos or previous position. That will be the current position of the cell, of that particular cell. So in temp, now we are basically updating the current cell's position to the new position, which is stored in new pos. Note that its previous current position is already stored in the pref pos variable. Now we completely updated its position including x and y. Now we update new pos with pref pos so that the next cell, when temp gets updated to the next cell, that can use this previous pos, this cell's position, and as its new position, right? So simple chain effect can happen. So now we update new pos with the current cell's previous position, and we do usual temp equal to temp dot next, and that should be enough to implement our cell by cell snake body movement algorithm. So what now we are going to do is we won't just call this function, this update cell positions every time, because why call it if the user has not provided any input, right, or any change in direction. So let's quickly get the user input. If key pressed, key, not is key pressed, should be is key down, actually is key down, key up, cur dir equal to 0. If is key down, key down, cur dir equal to 2. If is left, dir is towards left side, which is 1. And if is key down, is key right, so the directions are updated depending on the user input. And after we have done processing user input, what we would want to do next is simply call our update cell positions function. We will call our update cell positions function, and that should take care of updating the positions of the cells of the snake, or these cells of the snake body, every time after it evaluates the inputs, right? So the thing is that if the user has not provided an input, the snake will keep moving in the direction that it was moving previously, right? So if the user provides no input, the snake will simply move to the next position and the next position and so on in the same existing direction. If the user provides the input and it actually changes the direction of the snake, then we will update the cells of the snake body accordingly. So now let's see if this works. And we don't have anything on the screen, so the square is gone. There is no square. Where is the snake that we just created? I ran again and yet there is nothing. So what's actually happening is that this update cell position, which is calculating the delta and then updating the head and then moving the cells of the snake, which is right now just the head cell, it's happening so fast because it's happening every frame, and the default frame rate of Raylib is, I believe, it's 60 times. It updates the screen 60 times per second. Basically the frame rate is 60, so that's too fast for our eyes to perceive, right? So that's why even before we are able to see the snake, it just goes out of the screen boundaries and it's lost forever, right? So how do we fix it? We will fix it in the proper way soon by adding a delay between every frame update. For now, very simple way to fix it is we will do a hack. We'll do a sort of, I can say, cheating, and after we have initiated our window, we will set the target fps to be 4. That is extremely poor fps, right? It will update the frame, it will update the screen 4 times a second, which is really poor fps. So now it's just for the demo purpose. If we now try to run, you can see the snake, right? And the problem that you will face while if you're running this using this fps hack, you will see that if you press the left key or the right key, the right arrow key, if you press it too fast, it won't even capture your input, because it's just the frame is just getting updated four times every second, right? So you will have to keep it pressed. If you let's say if you want to move up, you will have to press the up arrow key for a longer period of time. Same for all the arrow keys. But now at least you can see that a snake indeed moves, right? It is moving, and I'm able to control the snake's direction using the arrow keys as well, right? So let's try to fix the frame rate thing in the proper way, right? So that we do not have any jitter and we do not touch the fps, but we are able to add some delay before updating the position of the snake. So what I would want to do, or what I would want to happen, is that the snake's position should get updated every, let's say, every 0.1 second, right? 0.1 second or 0.2 second, we can tune that. So what I want to do is that every the snake's current position should hold for at least x seconds before it gets updated, right? And we need to, so right now it's getting updated at fps rate, like frames per second rate, but we need to reduce that. Okay, so first, to achieve that, first I'll have a variable called float timer val, which I'll for now set to 0.1. And when the game starts, I'll create another variable called float update timer. And right when the game starts or restarts in init game method, what I'll do is I'll update timer equal to time val. Now that we have the update timer initialized, what I'm going to do is, just after I have captured the input, I'll have a if condition which says if update timer greater than 0, which means our update timer has not yet become 0. What I'll do is I'll subtract it by an amount equal to the time passed since the last frame was drawn. So this will roughly be equal to the time between two frames, right? Or rather, the time for which a frame persists and then it goes to the next frame. So if your thing is running at 60 fps, this will be 60 frames per second. So it will be, this amount will roughly be equal to 1 by 60, right? So every time that 1 by 60th amount, roughly that 1 by 60th amount of a second will get subtracted from update timer, and that will happen as long as update timer is greater than 0. If it ever goes below 0 or becomes equal to 0, that's the time, that's when we'll know that 0.1 second or whatever delta that we decide, in this case time value is 0.1 second. So that's the time, that's the moment we know that 0.1 second has passed, and is the time you update the, not draw, but you update the cells positions, right? Or you update the snake's body cells positions, right? But not just that, you need to do one more thing. You need to reset the update timer to time val as well. Time or val, yeah. After doing this, we won't need to do this anymore. So we can simply get rid of this. Why? Because now we are making sure that on every, like, we are waiting at least for 0.1 second before updating the cell's position, and 0.1 second is enough for our eyes to perceive the movement of the snake. And we can also play with this value to change the speed at which the snake is moving, right? So let's try to run it. Okay, looks like there's some issue. So I did a mistake here. It should be minus equal to. Now let's compile once again. Yeah, now you can see that it's moving, and we can see its movement, and also I can change its direction, and I have no issue controlling it. I don't have to press the arrow keys for long period of time, and it's nice and responsive. And the speed 0.1, I like. The speed is a bit fast because it's 0.1 second. It's we are updating position every 0.1 second. We can play with it to slow it down and things like that, but the thing is that it's working as expected. So next, let's come up with the food particle generation, and it's drawing it in a cell randomly, right? So we will generate a food particle and we'll place it randomly in a cell so that the snake can go and eat it. So I'll quickly define a function called void generate food pause. So how do we decide where the food particle will be generated or where the food will be generated? It's pretty simple. Of course, the food particle will also be a cell which we will shade black. And now the question is, which cell should we shade? So we'll randomly select a cell. So we will randomly select a x coordinate. We will randomly select a x coordinate. We will randomly select an y coordinate. That will become the position of a food particle. So selecting x coordinate would be like generating a random number between 0 and the maximum number of cells on the x-axis, and generating a y coordinate would be choosing a random number between 0 and the maximum number of cell on the y-axis. So let's do that. So these are just some quick variables. Okay, looks like I did not never created this num cell x and num cell y things. I'll just create two variables here. Using macro directly in that computation was giving me some trouble, so I decided to go with usual variables. Maybe I was doing something wrong, but I didn't want to spend much time trying to find out what was going wrong, so I just went with two separate variables. So now this function should be sorted here. Num cell x and num cell y. We have both now, and so what will be the pos x, or the x coordinate of the newly generated food particle? We will use the random function. So rand modulo and x minus start plus 1, and this is a very standard formula. You can simply Google it. You will get multiple links to generate a random number, a random integer between two numbers, or between a lower limit and an upper limit, with the limits being inclusive. Once again, rand modulus, and this time I'll use the y variables. Plus start. So food, okay, I'll need to generate a global food variable as well, but that's just a vector 2. So food pause equal to vector 2 dot x equal to pos x, and dot y equal to pos y, and it will be parentheses. And where we will call it from, will the first instance of it will be, of course, it will be called from the init game function. So let's just once, oh, okay, we need to draw it as well, right? Otherwise, how would we able to see it on screen? So just after drawing our snake, we will draw another rectangle, 4.pos.x into cell width. So we'll do the same scaling thing that we did earlier. 4pos.y into cell height, cell width, cell height, and we'll call it black. And here we go. We have our food particle painted on the screen. It's randomly selected. Actually, if I just start our game once again, you can see it got generated again at the almost at the same place, I believe. Yeah. So that's because we did not do the time seeding before using the random number generation. Quickly let's do that as well. So there's a very simple thing actually. is rand time null. Now you can see that it's getting like getting it will be getting generated at different places. So here it got generated here. If I run it once again, it got generated here. If I do it once again, it got generated up here. Okay. Now comes the other fun part: how to make the snake eat that food particle. Basically, collision detection between the snake and the food particle. Not just collision detection, checking or validating when the next position of the snake will collide with the food particle, and if that's the case, then create a head at that food particle location and create a new create a new head for the snake at that particular food particle location. Let's do that nice and quick. So we'll create a new function called what will be the next, which will give us what will be the next position of the head after we have evaluated our input. So for that, I'll create a function called, it will return a vector 2 actually, so we'll call it vector 2 get next head pause. It's pretty similar to what we did while updating the snake head position. We'll have a del x. Actually, I could reuse this function there, but for now I'll just keep it like this, and then I can simply copy paste from here. I can copy paste this part as well, and instead of storing it in another variable, I can simply return it. So dot x equal to cell node head dot blah blah, and yeah. So simply the next position of the head. Now I'll generate another function called void check snake food eat, whether the snake is going to eat the food or not. So in this function, I'll create a position vector, or I'll create a vector 2 type of variable called next head pause, and I'll get the next head position. And now simple collision detection, but in this case collision detection will be very easy because we'll just check for cell overlap, right? So basically we need to check the coordinate of the whether the coordinate of the head and the food cell is matching or not. So next head pause dot x equal to food pause dot x, and next head pause dot y equal to food pause dot y. If this matches, if this condition matches, we will generate a new cell. And remember, if the head cell already exists, it will simply create a new head cell. That's it. The add cell function. Dot x equal to food pause dot x dot y equal to food pause dot y. So the immediate next thing I need to do after checking for collision between food and snake head is generate a new food particle in a new at a new position, right? Because again it will need something to eat, and that's pretty much it. That's our function. And so now we'll call it from, where should we call it from? We should call it from just after we enter the else part of our timer. So just after we are about to do this update cell positions, because we need to do it before we update the cell positions of all the body in the snake, because after you discard the old head and make a new head at the food cell, you need to move that head as well in the current direction, right? So let's say the snake eats the food particle and you generate the new head in the space that was in the cell that was previously occupied by the food cell. Now that head also needs to move, right? Just like the previous head. So that's why we first check if the snake is going to eat the food, and after that we do the update cell position thing, or rather after that we move the actual snake body. Okay, so that's pretty much it when it comes to eating the food. Okay, so now let's give it a shot. What I'll do is for the testing purpose, I'll make it 0.2. The speed, I'll just reduce the speed a bit, and now let's try to eat something. And look at that, the length of our body increased, right? The length of the snake's body increased, and I can keep eating. The snake can and the snake can keep eating more and more food particles or food, whatever you call it, and its length will keep increasing. And just look at how the snake's body is moving. This is what I was trying to explain on the drawing board. I can go any way possible, and the rest of the body cells will follow. The snake's head. So basically, the head of the snake controls the direction. That's it, and all the other cells of the body simply follows the previous cell's position. So I can move. I can go any way I like. Look at that. Isn't that cool to watch? So the length of the snake is increasing without any problem. And but now you will notice another weird thing that's happening. Look at that. I can change the direction of the snake, and it really makes it weird. If the snake is moving at, let's say, right direction, I should not be able to completely invert the direction to left. That completely destroys the effect, right? A snake cannot simply start moving backwards. At least in this game, in this old game of snakes, it cannot just start going in the opposite direction. So let's quickly fix that. And fixing this is actually extremely simple. When you are taking the input from the player, you just need to check what is the previous current direction. So if it is up, you need to make sure that the current direction is not down. If cur dir not equal to 2, only then make it 0. So if the snake is not going down, only then move up. So here it's just the reverse. If cur dir not equal to 0, only then, or if it's not moving up, only then move down. Here again, we will do the same thing, but for horizontal directions. For left, we need to make sure that it's not moving right first. Oh, I didn't give a brace here. If cor are not equal to 1, only then we allow making the direction 3 or right. Okay, now let's test once again. So the snake is moving right, and I cannot make it move left. If it's going down, I cannot go up. If it's going left, I cannot go right, and if it's going up, I cannot go down. That's it. So with the directions fixed, our game is almost coming to an end right now. We need to now think about the game over conditions, right? What can be the game over conditions for this game of snakes? So traditionally, the game over conditions used to be like when the snake hits the boundary of the screen. So when the snake's head hits the boundary of the screen, two things can happen: either it's game over, or it just wraps around the screen, like it goes out of the screen from, let's say, from the right hand side, and it comes back from the left hand side, and same for up and down. But in this case, we won't do the wrapping thing. We'll just make it game over whenever the snake touches the boundary of the screen, or crosses the boundary of the screen. So let's do that. And there is another game over condition. What if the snake tries to eat itself? What it basically implies in the game world, the snake basically crossing its own body, right? So the head of the snake crossing its own body. If ever the head cell of the snake comes into direct contact with any other cell of its own body, it's game over, right? Let's do that as well. So we'll create a function called void check collision and boundary. Will basically get a temp pointer to the head node, right? And now what we'll do is we'll do cell dot pause. We'll basically check if it's colliding with the if it's colliding or crossing the screen boundaries. So cell dot pause dot x greater than equal to num cell x, or head dot cell dot pause dot x less than 0, or head dot cell dot pause dot y num cell y, or head dot cell dot pause dot y is less than 0. So these are the usual, very usual screen boundary check conditions, right? We have done it multiple times in the other games, in the other videos as well. So now here we need to implement something known as a game over function, and then we can return from here. We'll soon come to the game over function, right? Let's get done with the collision checking and boundary thing. So this we are done with the screen boundary checking conditions. Next, what we are going to do is we are going to again create a temp variable, but this is going to point to head dot. Next, we already have a reference to head, and here we are taking a reference to its next cell. And starting from the cell which is immediately the next cell after head, we will loop over this next body. If head dot, basically I'm trying to check if there is an overlap between the head cell and any of its body cells, right? Again, that also is a valid condition for game over. Otherwise, see, we simply do temp equal to temp dot. Next, now we need to define the game over function. But to do that, first we need to decide the states of our game and the variable that will hold the current state of our game. So for that, so to define the game over function, first we need to define a variable known as the game status. This is nothing but a variable or a flag that indicates the current state of the game, whether it's running or it's game over, right? Next, what we need to decide before implementing the game over function is actually we can right away go and define the game over function. It's like game over function is nothing fancy. All it does is like void game over. All it does is sets the game state is equal to game over. That's it. That's all it does. And since we are doing this in game over in init game, in our init game function, the other thing that we should do is set, after everything is done, we should set game status equal to game running. Now, what happens when it's game over? Like something needs to happen, right, in order to make the players know that it is game over and they need to restart the game. So in this case, what I've thought of is I'll just pause the game, and I'll not draw the I'll not render the snake, but I'll simply say game over in text, written in text on the screen, right? Let's do that. And also, all this input updates and input evaluation and cell positions update and collision detection, everything happens when the game is running, not when it's game over, right? Because there is no snake, there is no movement, what we are checking for, right? So let's do that as well. So everything that happens here, it goes inside a if statement, which at the very beginning checks for the game running flag. Not this, but game running. If it's game running, if it's inside game running, then we evaluate the inputs. So this entire thing is now inside the game running thing, and only then we perform these things. We just close the if condition here. And the other thing that we need to do is we need to show the game over text when it's actually game over, right? So only if game is running, only then we draw the snake's body. Okay, I did a mistake here. I should have missed the key up thing. Right, and this thing should be here. And let's now move it inside this if condition. Okay, now it's inside this, inside the if. I somehow missed this, and then in the else part, if the game is not running, that's basically our game over situation because there is only two states right now. So we draw a text, we write game over. Where we write it, we write it somewhere in the middle. We nicely offset the x and y so that the text appears towards the middle of the screen by 2. I found these values by experimenting. So if you are changing the dimensions of the screen, you might have to change these ones as well. Minus 100, comma 36, comma black. So 36 is a text size. Okay, now I want to write one more thing. How now if it's game over, player should have a way to restart the game as well, right? So we'll say press R to restart, and we do once again the x coordinate will remain the same as game over text. The y coordinate will change. We'll have the same text size, which is 36, and color is black. That's pretty much it. So our entire input evaluation and position update is within the game running condition, and also when we are drawing it as well, we have put it under the game running condition, and we have said that the player can press R to restart. So we should keep our word, which means we need to take into consideration the R key as well in evaluation while evaluating. If is key pressed, key underscore R, what do? We simply check if game status equal to game over. Otherwise, it will keep on restarting the game over. Only then we trigger init game, and init game will automatically reset game status to game running. That's it pretty much for restarting the game on pressing R. Okay, that's pretty much our game over conditions. Let's play the game once to see that whether it's working or not. Make run. Okay, let it. Okay, for some reason it didn't work. Let's see why it did not work. So we are calling. Oh, so forgot to call this function itself. Let's see if what happens when it collides. Let's go up. No, it still didn't work. Oh, here also I didn't call the functions. Great. So let's test again. Okay, let's go up, and it's game over. Let's press R to start, and somehow it's two snakes. Oh, I know what's happening. We need to set the body of the snake to the head of the snake to null as well, so that the snake again starts from just one cell and not So right now, whenever since the existing head of the snake persists, it simply it's adding another head. So let's tackle that as well. And actually, it's not that actually we need to destroy the snake's body completely, or else those nodes will linger in the memory, which is not good, right? So we'll write a quick function to do that. We need to store the current node to be deleted in a temp variable so that we can get access to the next one, or else if we delete the existing node we can't go to the next cell or next node. So first let's update the temp variable dot next. After that we simply do free tell node, and we set the head to null, and we will call it from here. Cool. That should take care of this problem where another extra head was getting spawned whenever we were pressing restart. So I did not compile. Okay, let's go up. It's game over, and yep, we are back to a single head. Let's try to get this food. Okay, so it's a 3 cell snake now. 4. So okay, now let's try to do a game over thing, and yep, it got game over. And now let's try to make the snake bite itself. So now let's try to create a loop, and it's game over. So that worked as well. So our game over conditions are working as expected. Okay, so the final thing that's now remaining is creating our scoring system, right? So we'll increment the score by 1 whenever the snake eats a food particle. So we'll keep it simple. So let's do that as well. So first for that I need a variable to track the score, and we need to increment it as well, right? Whenever the snake eats a food particle. So that function is mostly check food eat, this function. Here I can simply do a score plus equal to 1, and we need to show the score as well, right? And that's not that tough. Again, just before going inside the game running loop, we want to print the score so that the score is always visible even if it's game over, right? Text format. So text format is just Raylib's equivalent of printf. I'm a huge fan of Raylib. I simply love it. Like, let me know in the comment section below what games you people make using Raylib, or what projects you people make with Raylib. Raylib is so simple and yet so powerful. You can do so many things with it when it comes to gaming or just drawing things on the screen and everything. Like, yeah. And also when we are trying to restart the game, we need to set the score to 0 as well. So here we'll do a score equal to 0. So yeah, we can see the score, and let's see it getting updated. Yep, 2, 3. So yeah, the score mechanism is also working as expected. And let's do a game over once. It's game over. I can still see the score, which is 8. Now if I do R, it comes back again. It again becomes 0, and we can start over. Awesome. Okay, so one last thing that I would like to do now to this tiny snakes game is the grid markers, like basically the horizontal and vertical lines, the grid lines. To me, it seems a bit too dark, and I would want to make it a bit lighter. That would give a very nice, neat effect to the game. Basically, it would make the nice, neat, and it will give a very nice, neat, and subtle effect to the game. So let's do that. So very quick and tiny thing. So what I'm gonna do is I'm simply, instead of just writing black here, I'll do vector, not vector 2 but color 0 comma 0 comma 0 comma 50, and here also I'll do color 0 comma 0 0 comma 0 comma 0 comma 50. Let's try to compile once again, and this is now how it looks. That's the final completed thing, final snakes game. Maybe now we can speed it up a bit. So it was earlier 0.1, right? Let's make it 0.14. So this is how it looks and feels. Feels pretty good actually. The edge, whenever the food particle comes in one of the edge cells, it's really a tricky thing to take. Basically get that food particle. You can do things like increase the speed after it, whenever it reaches certain score. Whenever the player reaches certain score, you can increase the speed by certain percentage or things like that. Yeah, so that's game over. I must have hit the boundary of the screen. Yeah, that's it. There's the tiny simple implementation of the classic snake game. And as I said, the implementation is it's a simple implementation, but it's not that trivial. Like, in the sense, you can't just keep moving things along the x or y direction, do x plus equal to 1 or y plus minus equal to 1. It's not that simple. The movement of the rest of the body cells apart from the head is what makes this implementation interesting. That 4 to 5 lines of code that does that swapping thing, basically that h minus 1 taking the position of h minus 2 taking the position of h minus 1 cell. That 4 to 5 lines of the code is pretty much the most interesting part of this implementation. At least that's my perspective. Remaining part of the game is just fun to build and play because it brings back those memories. As I mentioned, Snake is one of the first game that I ever played on in the old mobile phones, which was like the old monochrome mobile phones, and like Snake, Space Invader, things like that. So yeah, that's pretty much it for this video. Well, let me know if you also have implemented your version of Snake and how did you do it, what framework did you use, and things like that. So yep, that's it for this video. Hope you all enjoyed, and see you all next time.